The standard operating procedure for electrical troubleshooting and calculation involves a systematic approach to ensure efficiency and accuracy. For troubleshooting, the first step is to identify the problem. Determine the specific symptoms or issues that are being experienced. Secondly, gather information. Collect details about the system, such as its history, any recent changes, and relevant documentation. Thirdly, isolate the fault. Divide the system into smaller sections and test each section individually to pinpoint the source of the problem. Fourthly, perform testing and diagnosis. Conduct electrical tests like voltage, current, and resistance measurements to identify faulty components or connections. Fifthly, repair or replace any faulty components. Once the fault is located, replace or repair the component or connection that is causing the issue. Sixthly, verify the solution. Test the system again to ensure that the problem has been resolved. For electrical calculations, the first step is to identify a calculation that is required. Determine the specific electrical quantity that needs to be calculated, such as power, current, or voltage. Secondly, gather the necessary data. Collect the relevant numerical information like resistance, length, or time. Thirdly, select the appropriate formula. Identify the electrical formula that applies to the calculation required. Fourthly, substitute the values. Plug the collected data into the formula. Fifthly, perform the calculation. Use the appropriate mathematical operations to solve for the desired quantity. Sixthly, verify the results. Check the calculation for errors and confirm that the answer is reasonable in the context of the problem. Electrical practitioners should follow this procedure systematically to ensure efficient and accurate troubleshooting and calculation. This includes approaching problems logically and systematically, using appropriate tools and test equipment, documenting measurements and calculations, following safety protocols, and staying updated on industry best practices and regulations. By adhering to this standard operating procedure, electrical practitioners can effectively troubleshoot electrical systems, identify faults, and perform accurate electrical calculations. Approaching electrical troubleshooting methodically involves a structured process to efficiently identify and resolve issues. This typically begins with a thorough understanding of the system's design and operation. Firstly, gather all available documentation including schematics, wiring diagrams, and operational manuals. This provides a baseline for understanding how the system is intended to function. Secondly, conduct a detailed visual inspection of the equipment and wiring. Look for any obvious signs of damage such as burnt components, loose connections, or frayed wires. These visual cues can often lead directly to the source of the problem. Thirdly, interview the equipment operators or users to gather information about the symptoms they are experiencing. Ask specific questions about when the problem started, what actions were taken prior to the problem, and any unusual behavior observed. Fourthly, use appropriate test equipment to measure voltage, current, resistance, and other relevant parameters. Compare these measurements to the expected values to identify any discrepancies. For example, if a circuit is supposed to have 120 volts and you measure only 90 volts, this indicates a potential problem. Fifthly, isolate the fault by systematically disconnecting or bypassing sections of the circuit. This helps to narrow down the area where the problem is located. For example, if you suspect a faulty sensor, disconnect it from the circuit and see if the problem goes away. Sixthly, once the fault is isolated, perform a more detailed examination of the components in that area. Use specialized tools such as multimeters, oscilloscopes, and thermal imagers to diagnose the specific cause of the problem. Seventhly, after identifying the faulty component or connection, repair or replace it as needed. Ensure that the replacement component is compatible with the system and meets the required specifications. Eighthly, after making repairs, thoroughly test the system to verify that the problem has been resolved and that all components are functioning correctly. Monitor the system for a period of time to ensure that the problem does not reappear. Ninthly, document all steps taken during the troubleshooting process, including the symptoms observed, the tests performed, the components replaced, and the final results. This documentation can be valuable for future troubleshooting efforts and for tracking the history of the equipment. 10thly, always follow established safety procedures when working with electrical equipment. This includes wearing appropriate personal protective equipment, such as gloves and safety glasses, and energizing circuits before working on them whenever possible. Additionally, consider using lockout/tagout procedures to prevent accidental energization of the circuit while you are working on it. Electrical calculations are essential for designing and maintaining electrical systems. These calculations ensure that the system operates safely and efficiently. Here are some common electrical calculations and their importance. Firstly, Ohm's law calculations are fundamental to electrical engineering. Ohm's law states that voltage equals current times resistance, or volts equals amps times ohms. This relationship is used to determine the voltage, current, or resistance in a circuit. For example, if you know the voltage and resistance, you can calculate the current using the formula current equals voltage divided by resistance. Secondly, power calculations are used to determine the amount of energy consumed or produced by an electrical device. Power is calculated as voltage times current, or volts times amps, which gives you watts. This is important for sizing circuit breakers and determining the energy consumption of appliances. For example, a 120-volt appliance that draws 10 amps consumes 1200 watts of power. Thirdly, voltage drop calculations are used to determine the amount of voltage lost in a conductor due to its resistance. Voltage drop is calculated as current times resistance. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. For example, if you have a long run of wire and the voltage at the end of the run is significantly lower than at the source, this could indicate excessive voltage drop. Fourthly, conductor sizing calculations are used to determine the appropriate size of conductors for a given application. The National Electrical Code, or NEC, provides tables that specify the ampacity, or current carrying capacity, of different sizes of conductors. These tables take into account factors such as the type of insulation, the ambient temperature, and the number of conductors in a conduit. For example, NEC Table 310.15b16 provides ampacity ratings for various conductor types. Fifthly, conduit fill calculations are used to determine the maximum number of conductors that can be installed in a conduit. The NEC specifies the maximum allowable fill percentage for different types of conduits. Exceeding the conduit fill limits can cause overheating and damage to the conductors. For example, NEC Chapter 9 Table 1 provides conduit fill information. Sixthly, short circuit calculations are used to determine the amount of current that will flow in a circuit during a short circuit condition. This information is used to select appropriate overcurrent protection devices such as circuit breakers and fuses. Short circuit calculations are complex and often require the use of specialized software. Seventhly, grounding calculations are used to ensure that electrical systems are properly grounded. Grounding provides a low impedance path for fault current to flow back to the source, which helps to protect people and equipment from electrical shock. The NEC specifies the requirements for grounding electrical systems. Eighthly, motor calculations are used to determine the appropriate size of motor starters, overload relays, and branch circuit protection devices for electric motors. These calculations take into account the motor's horsepower rating, voltage, and full load current. Ninthly, transformer calculations are used to determine the voltage, current, and power ratings of transformers. These calculations are important for selecting the appropriate transformer for a given application. Tenthly, lighting calculations are used to determine the amount of light needed for a particular space. These calculations take into account the size of the space, the type of activities that will be performed in the space, and the desired level of illumination. In summary, electrical calculations are essential for ensuring the safety and efficiency of electrical systems. These calculations are used to determine the appropriate size of conductors, overcurrent protection devices, and other electrical components. The National Electrical Code provides detailed requirements for electrical calculations and installations. Always consult with a qualified electrical engineer or electrician when performing electrical calculations or installing electrical systems.